So let's talk about the basics of matter. We're going to talk about some properties of matter and then also the classification of matter. Um, so what is matter? Matter for us is defined as anything that has mass or volume. That's a pretty technical definition of what matter is. Um, so anything that has mass or has a defined volume will be defined as what matter is. Now, sort of a layman's term sort of definition for it is matter is like the stuff that everything is made out of. So it's the things, it's the molecules, it's the atoms that everything is made out of. Um, the air, a computer, any of those things, those are all what we define as being matter. Atoms are the basic unit of matter. Um, they're the smallest thing that retain its chemical properties, but um, those are sort of the smallest things that everything is made out of. Molecules are a little bit larger. They're a neutral group of atoms. They're connected with chemical bonds. You'll get into more of that later when we start talking about bonding in unit 3 or 4. So atoms are what matter is made out of. Matter is anything that has mass or volume. So what we're going to do next is we're going to be talking about sort of some properties associated with different types of matters, chemicals, and substances. So there's kind of two different categories. There are physical properties and there are chemical properties. Um, Physical properties are intrinsic to the matter. The word intrinsic is a word that means it just has it. So for instance, if someone is intrinsically motivated, they're they're just motivated. You don't have to sort of provide them with grades or anything else to get them motivated. If someone's intrinsically motivated, they just do it. So intrinsic just means it just has it. So these are intrinsic to matter. Generally, these are something that describe about the matter. So is it blue? Is it silver? Does it bend? Is it malleable? Does it not break? Or is it brittle? Those all describe something about the matter. So some examples are color, mass, the melting point of the substance, the boiling point, the shape, um, density, odor, solubility. All of these are the matter just has it, and they describe things about the matter, the chemical. Now, chemical properties are properties that are only evident when there's a chemical reaction taking place. So physical properties are about what describing the matter, what it is, and then chemical properties is how it behaves. Does it dissolve in water? Is it flammable? Does it rot? Does it decay? All of those are chemical properties. So does it react with water? Is it an oxidizing agent? Is it flammable? All of those are chemical properties. So matter can undergo either physical or chemical changes. Physical changes, they don't change what the substance is. They don't change the composition of the substance. So before and after this change, it is still the same substance. Examples of that are, well, typically these are reversible, so they can go back. They don't have to, but they can go back. So some examples are changes in state. So that would be like going from a solid to a liquid. So if you take ice and you let it sit out and it turns into a liquid, that's a change in state. And so because it's a change in state, um, it is still water before and after that physical change. Um, like if you stretch it or bend it, you change the shape of it, all of those are physical changes. They don't change what it is. Cutting a piece of paper, it's a paper before and after. You're just cutting it and you're just changing the shape of it. Now, changes to, that does change the composition of the substance. So before and after this change, it is different. It is something different from before and after. So it changes what it is. Um, so if the physical properties change, it is a chemical change. I think that's important to realize. So before it was a silvery metal, now it's a really, really brittle uh, orange substance. That is a change in physical properties. So that is going to be a chemical change. Examples of this are like rutting, rotting, or burning. All of these are examples of what would be a chemical change. There are 5 signs to a chemical reaction, a chemical change is taking place. Chemical change, chemical reaction, pretty much the same thing. They're used interchangeably. So 5 signs for a chemical reaction. Firstly, if there's a color change. So if it was blue and now it's clear, that's going to be a color change. And so that's going to be a chemical reaction taking place. If you form a precipitate, now this is kind of a different word, probably a word that you're not interested or not familiar with. Formation of a precipitate means that you take two solutions, so you have like something dissolved into the water, you dump them together, and it forms a solid. That's the formation of precipitate. The precipitate is the solid that forms. If you form a gas, so typically you'd see this just by bubbles forming. If you see bubbles coming up, you're talking about a formation of a gas. If you have an odor change, so it has to be a change in odor, not just does it smell, but it could have been smelly before and now it doesn't smell at all. But if there's a change in odor, that's also a change. And then temperature change. Now, temperature change, you really have to be careful with because you have to think about where does the heat come from? Where does that temperature change come from? If I were to um, you know, heats up a pot of water, right? That's not a chemical change, that's a physical change. But the temperature's changing. But that's because I'm doing the temperature changing. I'm the one providing the heat. I'm the one giving it energy. If I mix two chemicals together and it gets colder, that's a temperature change caused by a chemical reaction. It's not something that I'm doing. It's something that is happening because of a chemical reaction taking place. All right, let's next talk about how we classify matter. We can kind of classify matter as two major big big things that are different, and that's pure substances versus mixtures. That's the first thing. And then pure substances can be split more and mixtures can be split more. So here's how we classify matter. So we can classify pure substances as either being elements or compounds. Now, elements are very, very easy to look at. They only contain one type of element. So you only have gold atoms, right? If you have pure gold, you only have gold atoms, so it is an element. So it only contains that one type of element. Now, the way that I sort of pick these out is that if it's like something and it's found on the periodic table, it's the periodic table of elements, right? Only elements are on the periodic table. So if you find water, well, water's not on the periodic table. But if you find oxygen, that is going to be on a periodic table, and that is therefore is classified as an element. So an example of that is like graphite, which is what your pencils are made of. Graphite is just nothing but carbon and these really thin layers. So it is nothing but carbon, so graphite is an element. Now, compounds, on the other hand, they're still pure, so it has only these things in it, but they can only be split into simpler substances by a chemical reaction. So you can't separate them really easily. They're stuck together with chemical bonds, so these are pretty difficult to split. It contains two or more elements that are chemically bound together, and then that would be a compound, and it must be pure, so it can't have anything else in there. So two or more elements combined with a chemical bond, and then our example is water. Now it has to be just water, pure water. Another term for pure water is distilled water or deionized water. Those things mean the same thing. Essentially, it means that you've removed everything else and you have only water molecules. So only water molecules means it's pure water, and pure water is a compound because you have two hydrogen atoms and an oxygen atom bound together to form a chemical compound. So that's how you identify that compounds are compounds. The next you have mixtures. So mixtures can be separated into two separate categories as well. And the first one is called a homogeneous mixture. Now a homogeneous mixture, if you think about the prefix homo, homo means same. And so it's a mixture that's completely uniform. So it's the same throughout the entire mixture. If you were to look at it in two different spots, you cannot tell the difference between those two spots. That's how I sort of identify it and picture it. Is I take two samples and I take two samples out of it. I look at them. If I can't tell the difference, it's a homogeneous mixture. Another term for a homogeneous mixture is a solution. So if you ever see the word solution, that means a homogeneous mixture, like a saltwater solution, or really any other ones. Tap water is a solution. And which means it's a homogeneous mixture. It's got other stuff in it. Like tap water has chlorine ions, it's got fluorine ions in it, all sorts of other different ions. Those are all a homogeneous mixture. So another example that it could be a solid too is like is Jello. Like pure Jello, it's got nothing in it. So just nothing but those that just normal Jello. If you take two samples of it, you can't tell the difference in it, but you know that there's stuff inside of it. There's dyes, there's flavoring, there's gelatin, there's all sorts of stuff inside of there. But it is going to be a homogeneous mixture. Mixtures can also be separated really easily, or relatively easy, using physical means, a filtration system, or chromatography. So there are ways of separating out um, mixtures in some way. Then you have a heterogeneous mixture. Hetero means different, and so heterogeneous mixtures are not uniform throughout. My best example for a heterogeneous mixture is like a blueberry muffin, right? And a blueberry muffin, if you take two samples, they're going to be different. One sample could have a blueberry and the other one could not. It's not uniform throughout the entire mixture. Um, an incredibly gross example is this. I think it's Jello tuna salad. It's just really disgusting. But if you were to take two samples of it, for instance, from right here and right here, if you were to take those two samples, you would not be able. You would be able to tell the difference between the two because one could have, I think, a radish, an olive. I don't know what those things are. It's disgusting. Um, and you can tell the difference between the two of them. So therefore, it is going to be a heterogeneous mixture. So if you look at this graph right here, what I want you to do is if you want to pause, for each one of these, could you tell me whether or not it is a element, a compound, a heterogeneous mixture, or a homogeneous mixture? Now the mixtures might be a little bit hard to figure out which one they are. Just label it as a mixture and then we'll get to that here in a second. So looking at this graph, we can see on the left-hand side here, this has only one type of element. We have just these blue atoms here, only one type of element, and we have that only one type of element, so that is going to be just an element, not a compound. Here we have only green ones. It's diatomic, which means there's two of them stuck together. This is still an element. This is a compound because we have two different elements stuck together, but you have only that molecule. So since we have only that one molecule in the whole thing, it is going to be a compound. The one on the right here, this is a mixture. We have multiple different um, molecules or atoms, and they are just mixed together. Now, I can't really say whether or not this is a homogeneous mixture or heterogeneous mixture. You need to sort of figure that out on sort of a macro scale. So you'd have to like look at a whole bunch of it, not just what the tiny representations are. So we have element, compound, mixture.